Have you ever just stopped and thought about how any of this works? I mean, how does the rich, colorful, noisy world that we live in get crammed inside a machine? How does something as complex as a song or a photograph get translated into a language that a computer can actually understand? Well, that's exactly the mystery we're going to unravel today.
Think about it. That selfie you just took on your phone or the podcast you're listening to right now. At their very, very core, they are not what they seem to be. They're a translation, an illusion, really. So let's get into it and break down what they're actually made of.
All right, so the first thing we have to get our heads around is that we're dealing with two totally different worlds. First, there's our world, the one we experience. It's full of nuance and, endless variation. And then you've got the world inside a computer, which is super rigid, precise, and all about the math. The real magic of all modern tech, it lies in that translation between the two.
Okay, so here's the biggest difference. The analog world we live in is smooth, it's continuous. Think of it like a ramp. A sound wave, for instance, just flows seamlessly from quiet to loud. But a computer, it just can't handle that infinite flow. It needs things broken down into distinct, separate steps, more like a staircase. And that process, turning the smooth ramp of reality into a digital staircase, is what we call digitization.
So you might be asking, why even bother with all this converting? Well, because the payoff is, frankly, world-changing. A digital file can be copied 1,000,000 times, and that millionth copy is absolutely perfect, identical to the original. You can edit it, remix it, send it across the planet in a blink. This is the superpower that digitization gives us. To really get how this all works, we've got to go smaller. I mean, way smaller. We need to find the single, most fundamental building block, the atom, if you will, of all digital information.
And here it is. Meet the bit. It's the simplest possible piece of information you can have. It's a yes or a no, an on or an off, a true or a false. And for a computer, that's just a 1 or a 0. It's absolutely amazing when you realize that everything in the digital world is built from this one incredibly simple switch.
Now, a single bit all by itself, it's not going to get you very far. But the magic, the real magic, happens when you start stringing them together. Their power just explodes exponentially. With 2 bits, you suddenly have 4 possible combinations. 3 bits get you 8, and by the time you line up 8 little bits, you have 256 unique patterns you can make.
And that group of 8 bits is so important, it gets its own special name, a byte. Every kilobyte, megabyte, and gigabyte you've ever heard of, it all starts right here with this little guy. So, if a bit is like a single letter, you can think of a byte as the computer's first and most basic word. So we have our basic building blocks now, right? We've got our bits and bytes. But how do we go from a bunch of on-off switches to something we can actually read, like, say, the words on the screen?
So here's the puzzle. We've got 256 unique patterns we can make with a single byte. How on earth do we decide which pattern means what? How do we assign those patterns to represent the letters in a simple word like hello?
The answer is something called a character code. You can think of it as a universal dictionary that pretty much every computer in the world has agreed to use. It's a rulebook that says, okay, everyone, from now on the number 65 will always mean a capital A. The number 97 will be a lowercase a. It's just a simple shared lookup table. And when you look at this table, you can see that translation happening right in front of you. To a computer, hello isn't a word at all. It's just this specific sequence of 5 bytes. Each byte is just a code for a letter. It's all just numbers in disguise. Okay, so text is one thing, but what about the really complicated stuff? How do we use nothing but zeros and ones to capture the nuance of a beautiful sound wave, or all the vibrant colors in a photograph?
For sound, the main process is called Pulse Code Modulation. Now, that sounds super technical, but it's really just 3 simple steps. First, sampling. We take thousands of tiny little snapshots of the sound wave every single second. Then, quantization. For each one of those snapshots, we measure how high the wave is and round it to the nearest step on our digital staircase. And finally, encoding. We just write down the number for each step using our binary zeros and ones. That's it.
And of course, there's always a trade-off. If you take more snapshots per second, that's a higher sampling frequency, and you have more steps on your staircase for more precision, that's higher quantization, you get a digital copy that sounds much closer to the original smooth sound wave. The quality is fantastic, but the price you pay is a much, much bigger file. Now let's talk images. The fundamental building block for any digital picture is the pixel. If you zoom in really, really close on any photo on your screen, you'll eventually see that it's just a giant grid of tiny, single-colored squares. Each one of those little squares is a pixel. So, when you hear people talking about your phone camera's resolution, like 12 megapixels or 48 megapixels, all they're really telling you is how many millions of these tiny squares it uses to build a picture. The more pixels you have, the finer the grid, and the sharper and more detailed your image is going to look. Simple as that.
But wait, how does each individual pixel know what color it's supposed to be? Well, it follows a recipe made of light, red, green, and blue, or RGB. For every single pixel, the computer stores a value for how much red, how much green, and how much blue to mix together. And it usually dedicates one full byte to each color. That gives it 256 different shades of red, 256 for green, and 256 for blue. And when you do the math on all those combinations, you unlock over 16 million possible colors for every single pixel. Wild, right?
Okay, so we figured out how to create these beautiful, high-quality audio files and stunning high-resolution images. But in doing so, we've created a brand new problem. These files are absolutely enormous. Trying to send or store them would be a nightmare without one last crucial trick up our sleeve.
And that trick is compression. Now, there are two main flavors. Lossless compression is kind of like vacuum packing your clothes for a suitcase. It makes the file way smaller, but when you open it back up, every single original bit is still there. Perfect. You need this for things like text or computer programs. Then there's lossy compression. This one is clever. It strategically throws away tiny bits of data our eyes and ears probably won't even notice, making the file dramatically smaller. This is what makes streaming music and movies possible.
Here's a super simple example of how lossless compression works. Instead of writing out the letter A 5 times in a row, then B 2 times, and so on, the computer just looks for the pattern. It says, hey, I see 5 A's here, followed by 2 B's, then 4 A's. It's just a much more efficient way to store the exact same information.
And check out the result. With that one simple technique, we took 25 characters of data and squished them down to just 10. The new compressed file is only 40% of the original size. And the best part? We lost absolutely zero information.
So what's the big takeaway here? It's that everything, and I mean everything you see, hear, and read on a computer boils down to this. The entire, vast, complex digital universe, from your text messages to Hollywood blockbusters, it is all built on this incredibly simple but elegant foundation of zeros and ones. From this simple binary foundation, this on-or-off switch, we've managed to build a world of instant communication, breathtaking art, and nearly infinite knowledge. It really makes you stop and wonder, what's the next impossible thing we're going to build using just a 0 and a 1?